Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleased to have Prasad here again. He's here a lot. And he's going to be talking about the number of linear extensions of the Boolean lattice, which is joint work with Graham Brightwell.
No question. So I'll assume Christian will know what a Boolean lattice is. The simplest way to think of is as for any positive integer t, consider a set of size t elements, and consider the collection of all subsets of that set. Then you have 2 to the t subsets, and you can define an ordering or a partial ordering on that set using subset relation. So the empty set would be below everybody in that ordering if you denote it as less than. And more generally, given any partially ordered set, there's also a notion of the set of linear extensions of a poset. So what is that? It's simply a mapping from the poset to a linear order whose size is the same as the size of the poset. So you have some freedom in terms of the incomparable pairs of elements, and the question is, in how many ways can you take advantage of the incomparability and extend a given poset to a linear extension. So here's a...
This function then is supposed to be bijective?
Yes, it's a bijection from... Yes, it's a bijection that's...
the size of the set.
Yes, the size. Right, so it's from S to the size of S.
Okay, so is that what's called topological sorting in other contexts?
Yeah, what is topological sorting? I used to know. Yes, it's the same as topological sorting. And so, in general, a question can be, given a poset, a partially ordered set, can you estimate, or can you enumerate, or can you study the linear extensions of a given poset? And so in general, it's a hard problem, as it turns out, computationally and otherwise. And here, the talk is about a particular poset, as the title indicated, which is the Boolean lattice, which is something I've talked about. Yes, so this example, the baby example is, so if you take t equals 2, then this is the empty set, which is below these two, and these two are in turn below everything. And so the only freedom you have is between these two elements. They're incomparable. This is not a subset of that, or vice versa. And so in terms of number of linear extensions, you could place this below that or the other way around. Okay? So in general, what's in any poset, so here is how I'm mapping. The empty set goes here, 1 goes here, 2 goes there, and this goes there. So that's one linear extension. Here is another linear extension. So there are just 2 linear extensions for this. Yes? Yes. So what's So you want, what is a good way to think about it? Yeah, so here is the way I can give you, let me show a bound and give a simple way, at least for the Boolean lattice, which is what we can restrict ourselves. So there's a simple algorithm we can describe which gives you tons of linear extensions, actually. So I'll say in a second. And the little bit of freedom you saw in the previous example between those two elements, you can extend it to any collection of elements, which is called an anti-chain in the language of posets. An anti-chain. An anti-chain or an anti-chain refers to a collection of elements with the property that no two in the collection is comparable. So in the poset, you don't have that one is less than the other, or the other way around. So when you go to linear extensions of that, you could place them in any order you want. So it's like an independent set in a graph. So when you go to mapping it into a linear... Right. So you take these under transitivity. If x less than y, y less than z, then x is less than z. That's part of the poset definition. For Boolean lattice, you have much more. What makes it a lattice in this context is you need to have for any pair of elements, you need a unique greatest lower bound and a unique least upper bound. And when you consider subsets of a set of some size, the intersection forms one and union forms the other. That's what gives it the name lattice, but that's not so important for us at this time. No. This is, why is it called Boolean lattice? You could think of them as... Yeah, I mean, you could...
So, that is a Boolean. You just defined the Boolean. You didn't define the lattice.
Right. For each dimension t, there's only one Boolean lattice, namely the one. So you could have other lattices, such as consider over the set of integers, let's say, and under divisibility as the relation, then so x is less than y if x divides y. Then that would also have these lattice properties because you have the GCD and LCM, which give you the unique elements with the property that you want. And so that's another lattice. And this particular lattice, the lattice of all subsets of some set, is called the Boolean lattice. One reason could be because you can encode it as 0, 1 vectors of the appropriate dimension. That could be where Boolean is coming. Okay, but there's, like Rick clarified, there's only one Boolean lattice, and that's what I'm talking about. And in a different talk, you would call it the discrete t-dimensional cube or hypercube and so on. So an old question that probably others have asked, but in a particular paper of Shah and Kleitman, it was attributed to a question of Richard Stanley, saying how accurately can we determine the number of linear extensions of this sort of quintessential lattice or quintessential partial order. And there are two easy bounds you can obtain. And so this is not one of them.
Isn't this bound statement that make sets of smaller sizes come after 4 sets of larger sizes, then it's a linear order, and you can just have the order from the things that we want?
That's right. So that's That's right. That's why I had to pause and say that the easy bound is not this. Right, so Schaaf-Lightman proved a particular upper bound, which is that it's product of these binomial coefficients. I'll show in the next slide. I'll show in the next slide. This differs in a very simple way, which gives, okay, whatever you see. So the result, you might have noticed in my abstract, gave an improvement of this upper bound by making this 1/2 into a 3/2. So it turns out it's easy to get the first order at this level. If you take the log and divide by the size of the lattice, which is 2 digits, it's easy to get this. And so the question is, what is the second order? Okay, and the previous best known bound is that particular 1/2 log E. And I won't say anything about how they obtained that bound. But, of course, the natural thing, or the first thing that we want to ask is anything easy? And so what he said is the lower bound in that. So namely, can we always get linear extensions cheaply? So for any antichain, as I said, you could permute them in any way you want. So at the jth level, you have p choose j elements, that many subsets of size j. And they form an antichain. Two subsets of the same size are not comparable. So the product of the factorials is the bound that he mentioned. That's an easy lower bound. And also an easy upper bound is to say, if you think of writing down linear extensions by mapping these elements systematically, what you can observe is, so as I write here, to think of constructing linear extensions one element at a time. So at any point, the choice you have in terms of which elements could you put next form an antichain. That's because if at some point, right, so let's say proof by contradiction, if you have two guys which have an order between them, then the lower one must go before. The higher one cannot be simultaneously allowed or eligible. So what's eligible at any time is an antichain, and we know in the Boolean lattice the largest antichain has size t choose t over 2, and so just a very loose bound would be t choose t over 2 repeated as many times as the size of the linear extension. So that's also easy, that t choose t over 2 to the 2. And as I said, that gives you the right first order term. Okay. Right. So Schaaf-Lightman gave an upper bound that was 1/2 log E here. So Schaaf-Lightman gave the first. Yeah. And our contribution is to show that this is also the same term on the right-hand side, and so the only difference is in the third order term. Okay, any other questions? So let me. Yeah, because I don't actually fully understand it. Yes. But right, so what Schaaf-Lightman did turns out to be tight in some sense. It's just not tight for the Boolean lattice. So I'll make a comment on that in a little. So there's a generalization of their result to a class of posets, and under that class, their bound is more or less tight. Okay, so again, another way to look at the upper bound is that this product of factorials is the easy lower bound he mentioned. And so another way to look at our result is that there's an error term which is e to that 2 to the t6 log t over t, so the third order term is log t over t. whereas it turns out by doing a little more than just stacking them on top of each other, the anti-chains. Schaff-Lightman showed that you can get some third-order term that's of the order 1 over t. So that's sort of the gap between the two bounds. We also have an exact result in the sense of, or a tight result for when you have just a two-level poset. So this is a very sort of simple and uniform type poset. Imagine the order relation you have is such that you can put the elements in a class A or class B, and with the property that everyone in B has precisely D elements down from them, and then for everyone in A, they're precisely U elements up from them. So just, for example, if you took a slice of the Boolean lattice, you have this property for some D and right? If you take two levels. There's a bound we can obtain for that case, which is actually tight for this particular poset, which is you take disjoint union of D plus U elements at a time. So the number of these figures is n over D plus U. And each figure has a complete bipartite graph. In other words, the simplest way to satisfy that figure, namely take D elements here, U elements there, and then join everybody to everyone. This has a certain number of linear extensions. It turns out that number is equal to this. And so the upper bound you get from this proof technique is tight for this particular example. And this, it's not a miracle. It's sort of, or maybe it's a miracle, or it shows the power of what one can call as an entropy technique that Jeff Kahn introduced, or at least developed in some ways. And from that technique, it's not surprising to derive results of this type, at least for the two levels. So I won't spend much time on this. This is just to say, to challenge people like David Galvin, to say, if you apply our two-level result to the middle two levels of the Boolean lattice, you get some bound that apparently is better than anything that was known before. And so here, L of, by this I mean, this was actually a typo. I had written it Q to the T, and then I put this. I mean the two middle levels of the Boolean lattice. Okay, so let me briefly state the sort of the final or the most general theorem we actually prove, which gives the Boolean lattice case as a corollary. And the general theorem is that take any, going from two levels to more than two levels, take any poset that sort of sits on k levels, and in level j there are n sub j elements, total n elements. And it has this uniformity which may differ between layers. So everyone in J has dj of them below and uj of them above. Okay, but it could vary from level to level. So u1, d1, u2, d2 like that. And we get a certain upper bound for the number of linear extensions for a poset of this type. And it turns out this is a good estimate in the sense that the error term is really 2 to the little o of the size of the lattice. every time you have a certain harmonic sum of these degrees satisfying some condition. But the reason I wanted to mention this generalization is that, so the specification of these degrees turns out to be crucial, and that's basically all the information that we use besides the nice, the regularity that the Boolean lattice has. And the information about the degrees is necessary for our bound. What do I mean by that? So let me go back to a comment I made before. Which was going to be a final remark, but let me cut to sort of. So Schacht-Lightman had this, had an upper bound which was n choose j raised to n choose j and product over j. And I said that is tight under some class of posets. So if you wanted to ask the question, suppose all you know is that there's a poset with n1 elements, n2, n3, and so on, and I'm not telling you anything about degrees because it could be crazy, then it turns out this is about the best you can show. First of all, their proof was extended to a class of posets, that this is a valid upper bound for the number of linear extensions for any such ranked poset. And by taking some example like this, which is, this is a chain of k elements and another disjoint chain of k elements and so on. So there is some extremal example, extremal up to smaller order terms, that shows that such a bound could be tight. But we know for the Boolean lattice, Schacht-Lightman is not tight up to the second order term, for example, right? And so this is just going back to what I said before, namely that if you don't use the degree information, then you could not hope to improve Schacht-Lightman. We do make use of the degree information, and we do improve it. So that's sort of, so that's all I wanted to say about Schacht-Lightman. And what class of poset? There's a class known as LYM for an acronym of 2 or 3 people, I don't remember. But it's fairly simple and actually a nice definition, and Boolean lattice fits that definition. It is an LYM poset. An LYM poset is that for every antichain or independent set, for every antichain you have some average weight condition. So give to each element in your poset the weight equals to 1 over size of the level in which the element is sitting. So if x is from level j, give it weight 1 over nj. And for every antichain you want that the sort of the average size is at most 1. If that's satisfied, then you say it's an LYM poset, and they have some nice properties. And the Boolean lattice is an LYM poset.
So does that example of
So in this example, you would put, so it would be k over n. Yeah, it's equal to 1. Yeah, that's what you're saying. Yeah. It's just, right. So this is k over n, and then you would multiply just each of, right. Actually for this, any antichain is basically something like a maximal antichain is somebody from this chain, somebody from there, and so on, right? Because you cannot take 2 from the same, they're comparable. So it's easy to check for the maximal anti-chain, it's exactly equal to 1. Yeah, so this is an LYM poset. Yes, and for that, whatever answer you get turns out to be close enough to that product of nj to the raised to nj. So that's but if you include the degrees, so I have basically a couple of open questions, and if you include the degrees, we don't know for the general k-level problem what sort of poset maximizes the number of linear extensions. Okay, you include this degree information, and it doesn't, we give up something. Although we get the second order term right, we give up something in the proof, and so it doesn't fall out of the proof as to what sort of a poset maximizes the number of linear extensions under the constraints that you have nj elements in level j with uj up degree and dj down degree.
In what context is that
I think I want to say maybe correlation. I'm not sure. Actually, so
because you want kind of maybe like an analog of that, something like that.
right. So yeah, I'm not, it might have come up independently in common source, but the reason I mentioned correlation inequalities was some of FKG type inequalities were extended to, which you can state for the Boolean lattice, 4 functions were extended to LYM is why, but it may not. Also that.
But there's nothing FKG-ish.
Right, as far as I know. Yeah. But maybe you incorporate it into a probability measure.
Right.
So. Also, I should say that Shaw-Kleitman result for the class of LYM posets was also derived as a corollary of something Jeff Kahn and Jung-Han Kim had done in part of Jung-Han's thesis work, I think, in answering some question about sorting from partial information. If you have a partially sorted list of whatever, how many more comparisons would you have to do to make it so? If you don't have any information, then you have certain n log n type comparison argument. Okay, so the other question is going back to the computational aspects of this. So I mentioned this problem is hard in general, and sharply hard or something, and David Wilson can tell you how much time it might take if you want to count approximately using a markup chain type method. So people have fast MCMC ways of getting to that. But you can say, for the Boolean lattice, it's a specific lattice. Is there a simple algorithm that spits out the actual number? I'm not sure if it's known. Okay, so the rest of the time I'll first spend just 5 minutes or less than 10 minutes about entropy, and then try to give you a proof for the two-leveled poset theorem, and that's very much like a proof of Jeff Kahn's for counting independent sets in bipartite graphs. And then David Galvin and I extended it to a theorem about counting graph homomorphisms from a bipartite graph to an arbitrary graph. So it follows that proof technique. which I will illustrate after going over these entropy. So this is just the definition of entropy of a random variable, or a discrete random variable. And conditional entropy is defined using the conditional distribution. So I'm assuming this is familiar to people. So I guess the 3' and 4 are the only somewhat interesting facts I want to mention. So the first one is that the entropy is non-negative and is at most log of the size of the support. And there's a chain rule which gives subadditivity. So 3 says giving some information cannot hurt us, if you think of entropy as some measure of information. Or if you think of it as uncertainty, the amount of uncertainty in the random variable x can only go down if you're given some information. And 3' is actually quite useful in all these proofs. 3' says it's a relaxation. Basically, sometimes you'll find yourself in a situation where you know too much information in terms of the conditioning you see, but then you know how to handle. And so if you relax it by conditioning by some other random variable, which is determined by y, then you have this nice inequality. And finally, this last inequality, which is also useful. So for the joint entropy, you can write using the chain rule these two, h of x plus y given x, or the other way around. And so you can use this equality and the fact that this is, say, one of these is non-negative, this is non-negative, to say entropy of x is at most this. And this is the step that usually requires cleverness in our proofs, or using information about the problem, because so typically you have this on the left-hand side and then you're trying to come up with a y. So there's no y on the left-hand side, but you have to invent a y that helps you in terms of bounding the entropy of x. It should help in the sense you don't give up too much when you go from here to there, which means somehow knowing y should allow you to control entropy, but y itself should not have too much entropy. And that
I can look at 4
yeah.
as kind of a lower bound complement 3. So is there an analog? Is there a 4' which will give you a lower bound for complement?
Right, actually, so right, so 3 shows, thanks.
3 and 4 together.
So 3 and 4.
The upper and lower bound on.
That's right.
Right, that define that.
Right. So the point is to come up with a y that has small h of y, because that's the gap between them.
Right.
Yeah.
And
your
then
question
one could try to do the same thing with 3'. Like
yes.
you could say that h of x given y is greater than or equal to h of x given b.
Yeah. So you could.
Something. There would be like an apple. There would be
Yeah.
like a 4'. Or should it be like
So everything, all the facts I show, you could do under additional conditioning, and that we do actually.
I wouldn't see how to do 3' because that's not analog of the proof form.
well, you can have a chain rule based with the intervality condition.
So you want to bound this by this plus. So somehow you have to relate. I think y given z. Z given y is 0, but y given z.
But y
And
given b, and then you could write in somehow be passing
yes.
off a quantity which has to be h of y.
Yeah.
for 3 prime, you just need x, y, z to be a Markov chain. You don't need y to completely determine z. And this is called data processing equality.
Yes, yes.
And so, and for 4 to be equality, I just think that x determines y, and then it's always an equality because x comma
Yes.
y is equal to x.
Yes. So in this one you have, yeah, this equality 0 would show that equality. And that happens also actually in our proofs. See, we have somebody from EE background. Okay, so the last but crucial fact is something you might have heard people mention. It's been used in a few results now, which is a refinement of subadditivity. It's probably the first thing that didn't come out of EE. Lot of stuff is from EE. So this is from a paper of Chung, Graham, Shearer, and F, I'm forgetting. That, yeah, so the result is that if you have a collection of random variables, x1 through xm, and then you have a set system, or you have a way of grouping them into sub-collections. So for A, a subset of those indices, when I say x sub A, that is the collection specified by the indices in A, okay, xi for I. And and by entropy of x sub A, you were thinking of entropy of this joint random variable. If you sum over the sets in your set system script A, then, of course, h of x, at most, sum of this is easy. It's basically subadditivity. But this lemma says it's at most 1 over d times that. Anytime you have a script A with the property that every one of these is covered by at least d members of the set. Okay, so in this summation, if you count every x sub I at least d times, then you get to divide by d. And that turns out to be quite powerful in all of these applications. And restricting to singletons is the usual subadditivity where b equals 1.
So, is that all?
Sorry?
Shearer's lemma hard to prove?
Is it hard to prove? Yes? No? Yeah, it's I think like I think it's like the local lemma too. Once somebody comes up with it, it's not so hard to prove. So that's a proof. I won't go over, but that would be a complete proof. Should I go over or skip? So this is not how he proved it, but this is actually the way I showed was not even how he formulated it. I think Jeff Kahn formulated it that way, and then this is Radhakrishnan's proof of Jeff Kahn's formulation of Shearer's lemma.
This is Prasad presentation of Radhakrishnan's proof of Kahn's formulation of Shearer's lemma.
Even on his last day, he gets trouble. Okay, but there is a nice, clever, slick proof of that. Let me not. Yeah, so there's one more idea we need for our stuff. So as you'll see, there's nothing really original in all of this. So what I think the key thing, we were stuck once we decided to use this entropy idea after the first line. But the thing that I think got the whole thing going and the ball rolling was that turns out linear extensions are pretty messy to work with. But instead, if you look at just the order preserving maps, and now we don't require that it's a bijection. So map it to some large or small universe and allow equalities if you want. Okay? So consider functions from the poset to 1 through m, where if x is less than y, f of x be less than or equal to. So you could map everybody to 1 if you want to. If you want it to be. Okay, and this came again, as I said, from something I had seen in a paper of Larry Shep, going back to correlation, XYZ inequalities, which were motivated by the FKG inequality. In that context, he used the order preserving maps to work with actually linear extensions. And then by taking m to be suitably large, you're able to get information about the rate of linear extensions. Okay, so it's very convenient and the perfect thing we needed. So that's one. Okay, so I'll try to outline the proof of the two-level.
So does your log come from the difference there? From the, when
The
you look at
log
the bound,
t over t, you mean?
yeah, log t over t.
That's a hard question.
I'm wondering how much you lose by
yeah.
relaxing
Wow,
it
so
by
I know.
It certainly makes it nice. I'm wondering if that's where the log is coming from. Maybe the log is right.
But also you could lose something because you're getting right results for full sets which are clumped.
Right.
And the linear lattice is nice and small.
Yeah, there is a different approximation. Or there's a place where we give up something by just maximizing, with the constraints we put in, just the degree constraints. There's a little Lagrange multiplier maximization. That's where we think. If we are losing, that's
Yeah,
where.
I mean,
right.
log t over t making it right at the time.
Okay, so in terms of order preserving maps, what we proved that for the two levels, I had no idea I would show colors. I would have brought all kinds of paper. So A and B are the two levels again, and the number of order preserving maps we show is some stuff raised to n over d plus u, where, remember that my extremal example was, it was a collection of n over d plus u of these gadgets. So it's whatever number of order preserving maps of that one of them raised to that, because it's an independent problem, product of that. That's how we prove it. I'm not saying this should be immediate. I hope it's not. This is kind of what I'll try to show proof of. And this, whatever stuff you see here, is not hard to see that that's actually the number of order preserving maps from this guy to 1 through m. That's an easy computation. Basically, you say, ask yourself, where is the lowest anybody from here is going to go to? Suppose that goes to j. Then all of A has to be below that. Okay? So all of A going below that is j to the d, because there are d elements in A. There are j choices for each one of them. These are order preserving maps, so I could choose to put everyone at 1 if I want. Okay, so that's j to the d. And the number of ways to send the top between m and j so that the bottommost is at j is sending them without being careful, but then subtracting those maps where I send everybody only here. Okay, so there's a simple computation that shows. Yeah. Yeah, and so this stuff like this is much simpler. so I can illustrate the 3 prime or whichever entropy fact I mentioned before with this example in mind. For example, if you're looking at where, maybe I'll come back in a second. Okay, so first of all, we have a completely combinatorial problem. Where is randomness or where is entropy? But that's not hard to guess. The first line in all these proofs is to take whatever you are trying to count uniformly at random from the set you're trying to count, so that entropy of that random variable is equal to log of the size of what you're trying to count. Okay, so F for us is uniformly at random from the set of order preserving maps from P to 1 through M. And so there's a little bit of notation, but bear with me for a second. So U of X is U for up, I guess. So the people, so again, P is just the 2-level poset. For X in A, U of X is everybody in B that's above X. And we know there is U of them, little u of them above everywhere. And Y sub X is a random variable that's minimum F of U sub X. So for a given X, Y sub X is where the lowest guy that's sitting above X went. F is sending people to 1 through M somewhere. And Y sub X tells me of the people that should be above X, where the lowest. Because, so going back to the relaxation inequality for entropy, that if Y determines Z, then entropy of X given Y, blah, blah, blah. This is the kind of thing that's useful to bear in mind. Suppose you're conditioning on the top level, and you're trying to bound the entropy of the bottom level. Then knowing everything about the top level is more than you want to handle when you look at, say, entropy of where X went. Just the information of Y sub X is really relevant because X has to go below that. Y sub X tells me the lowest anybody that's sitting above X went. Because it's order preserving, F of X has to be less than or equal to F of this guy, right? So if I'm looking at the people that are above X, and if they're all over the place, all that matters to me is where the lowest one is, because X has to go below that. Between 1 and that. And so when things get complicated, what we do is the entropy of something like that, we just bound by saying it's log of that length, 1 through wherever the lowest of the ancestors went. Because the entropy is at most log of whatever. Okay, so that's the kind of thing that we do. So, again, because F is uniformly at random from a set of this size, there should be a size, this is equal to that, and then you break it into, using the chain rule, entropy of the top plus entropy of bottom given top. And bottom should have been B, but sorry about that. So B is sitting on top, otherwise it would have been coming. Okay, so let me show the last one. So I wanted to show where the shearer is used in this. So we look at the entropy of F sub D, which is the entropy of the top, where the top elements went. And associated with each element in the bottom, there is a set U of X. And that's the set system from Shearer's lemma that we're going to use. And we know everybody on top is covered by at least D from the bottom. Exactly D from the bottom. That's why it's 1 over D of that. Okay, so that's just.
It would be a terrible balance, but it could also be a different it weren't uniform degrees, it could still do this thing like a
Yeah,
degree.
as long as minimum degrees, yeah. And then entropy of each of those you bound again using this chain rule, and here is where I said when you're trying to bound entropy of f sub x, all that matters is really where y sub x is, namely the lowest somebody above x max. So I guess to sort of wrap things up faster than whatever. So to bound the entropy of y sub x, we just wrote down by definition what it is. It's equal to, you see the definition of entropy, where px of j is basically the probability that y sub x equals j. And you have no idea what those probabilities are, but there's a Jensen's, inequality magic that lets you throw away or take those probabilities inside and get rid of them. So that's not a problem. And this step is showing how if you know the lowest went to j, then the entropy of this is no more than log of the total number of order preserving maps that send the top guys in such a way that somebody from above x went to j. Okay, so this is just from some global bound on entropy or conditional entropy. So there's nothing fancy going on, and as I said, you end up with these probabilities which you don't have a knowledge of, but then use Jensen's inequality to let them cancel each other. And yeah, so that's sort of a quick sketch of the proof. I'll say a couple of words about what we have to do for the full problem, for the general problem. Of course, we do induction because we can do it 2 levels. We have to go k levels, whatever. And that's where things get a little bit complicated. And so it's somewhat technical. The only other thing that we had to invent was do some kind of, I don't know, coarse graining or whatever. So take 1 through m. You're trying to count order preserving maps that map 1 through m. But break it like an IKEA bookshelf into a certain number of S levels. Okay, so for some parameter S that you'll optimize later. Meaning, so if you're in the first, however many levels, you treat it as the same level and so on. And it turns out you can, later on we have to optimize all these parameters, S, M, and so on. But that's one sort of an idea. And B sub x is just remembering sort of the bookshelf that somebody above x went into. Not necessarily f of that somebody, f like what I called before, y sub x, which is f sub u of x. Instead, just remember it at this level. So this is what you would care to remember, but remember only its index.
So how closely does it turn out that you
Right, I'll
lump
show.
a lot of them together?
Yeah, I'll show in just a minute or so. And again, just some simple bounds on this random variable, which you have to work with from below and above at the level of this indexing. Seem to work. So how close, how tight?
When do you use coarse graining in physics and argument? Usually with the entropy estimates that kind of blow up when you use coarse graining. Is that what we're looking at? Why do you have coarse graining? I don't see
Right, actually, so, yeah, in our case it was more because it turned out we could get away with that. We tried to do, so we wanted to do with just some bounded number of levels, given that. So m equals 2 and so on, they correspond to particularly nice things. So we wanted to have just bounded number of boxes. But for the induction,
doing an induction over the number of levels or not?
yes, we're doing
And
an,
you want just the thousand?
no, so those are k levels we're doing induction on. Yes, we have that. But this bookshelf thing I'm talking about is splitting 1 through m, which in the end should be somehow 1 through 2 to the t. For linear extensions, that's what it should be. Right, so m is going to be huge. Has to be at least 2 to the t. That's going to be very large. We'll get m 10 to infinity. But then you want to say, in terms of if x goes here, how many neighbors does it have? What is the up degree? Up degree of a certain thing. So it's like if those went randomly from 1 through m, what's the range they will span so that x could go below that? Yeah,
I kind of understand that, but I'm just trying, because like in hindsight, when I look back on a proof in which I've done coarse graining, I see where the entropy or some estimate would have really blown up without doing that. And so
yes.
maybe later you could point out what, if you see what would have blown up.
Right. Yeah, some of the, I don't know if they would have necessarily blown up, but, right, maybe.
Okay.
Right. So it
Because
wasn't.
you're telling me that often in physics, people, when they do coarse grain,
Yes,
it
it could.
turns out that people do sort of infinitely many steps in this coarse graining, but actually, it's mostly it's actually just one step of coarse graining.
well, when did they do?
Yeah, that's all. Right. In our case, that's all we're doing, just one step. So let me just point out this particular place where we are giving up something, I think. So the induction on many levels is that if you write down the entropy of the full order preserving map by the chain rule, you see where the kth level went, and then given that where k minus first and so on. And so given j plus 1 up to k, you can, of course, collapse some of these and write it this way, right? Collapse the chain. And the induction proof is based on this claim that this we're able to bound given j plus 1 and k in terms of x in aj, right? Because that's the immediate one. And these levels 1 through s of the bookshelf. And this is the probability that the lowest element that sits above x went into the shelf b sub j log some term. So we end up with some mess. So this mess was incredibly messy, or even more messy when we didn't try to put it into this bookshelf. We had no way of. So this is probably where I would have to say, this is the reason we had to choose S levels and then optimize over S. I mean, it was not all clear what S to choose and then do the proof. So, but it very much comes from the calculation. And whether it's needed, I'm not sure, because it's not like we were stuck with this problem for 2 months and then finally somehow they solved it. We weren't stuck for that long. And but anyway, in the end, we don't know these probabilities and so on, so we had to maximize something like this expression, which I found out with some simple case of Cobb-Douglas model in economics or something like that in your calculus books. And, but it's a simple thing to maximize. What this is saying is, if you know n sub I books have to go into the ith level, and you know the total height of the bookshelf, okay, and you know you have to make k shelves, how to do the separation between the levels. And of course, you should do proportional to how many books are going to go, roughly speaking. And that's the kind of maximization that tells you what the right thing to do here is. But it's a simple problem. However, that's the step where we're probably giving up something, because we just we only use the degree information and maximize at that point. So just to show more concretely, you have to maximize product of a bunch of things like that under the total number of books going to be n, and then however way you separate, when you add up all the separation, you should get something like s plus k minus 1 as the total height of the bookshelf and so on. So that it's a fairly simple.
So what did you do? I mean, what's the outcome?
Yeah, so again, these are probably not as well. For the Boolean lattice, yeah, so R is this inverse degree. So R is summation nj over dj. It's the harmonic sum of the degrees. But I think what would help is if I show what these parameters. So S is kn over R. So let's think k is log n for the Boolean lattice. Right? N is 2 to the t, k is 2, t plus 1, and so on. So that's n log n. And R is n over log n. So log square n. Yeah, so yes, so R is actually t. R is n over log n, and choice of S is log n over R. Yeah, so log square. And that's the, let me put this up. So that's it's the log square, that's the t squared here. Because n, I wrote them as n is 2 to the t, so this is like log n and log square n. Anyway, so but that's one place. But maybe if we repeat that, we gain something. I don't know. I don't know if we...
Doing like a multi-scale
Yes.
course grain
Yeah.
instead of just
Which I had never
one step.
thought of. I was happy with the answer we got and with the theorem we derived, but I wrote to Stanley saying, hoping we solved his problem or answered his question, and then I got something that made me feel very modest. It's nice to see there is some progress after so many years. Yeah, so Stanley wants more, I think. Anyway, I'll stop there. What's that? Like I said, there are challenging problems for audience, people in the audience. Yeah, so they're now, this was a result of Kahn that motivated David and me to extend in this way. But in these, we're probably getting sort of, next to what's best possible, or what, anybody that's living could prove, or something like that. What I mean by that is we're estimating very precisely at the level of log divided by the size. But you can ask not for asymptotic in the exponent, but downstairs. You would like a number times 1 plus little of. For that, for the question of number of antichains of the Boolean lattice, just counting how many antichains you have. This is a famous Dedekind problem that the second best result was derived using this proof, although it was known using a proof of Kleitman-Markovsky. Jeff Kahn re-derived it using the entropy approach. And so it could be that our result is, in that sense, second best, and the best result must come from much more hairy, much more combinatorial hard work that Saposhenko and some others have done. And David is probably the one that understands those best. Okay, have a good meeting.
For these problems, one of the biggest challenges is to know when to stop.
Yeah. Not for me.
Well, you overcome that.
So what are you going to be talking about?
Yeah, you come prepared to harass me.
Right, right.
Yeah, but no, in fact, I was trying to compliment him. This is the right one. Where is this method of
So Scott, you're kind of, how long are you going to do it?
If you look at
Well, we might actually be around.
classical volume,
Oh, yeah,
to
yeah.
compute
Yeah.
the linear extensions. So for the Boolean
Yeah,
lattice,
so I'm still around.
so that polytope, I mean, the Vinci is just the long ideal
Yeah.
Yes,
of the
yes.
poset. So that's I mean, like,
So,
would that be
yeah. So, yeah. So,
computing the number of long ideals and then using that to approximate the volume
and then to get a count.
and then to get a
So, what's interesting? Oh, it could be minor. So, Graham Brightwell did that. So, Shaw, Kleitman, Brown, upper bound. We know 3 proofs of it. Shaw, Kleitman. Brightwell gave, the way we did this was Brightwell gave a beautiful exposition of all those results going into the polytope, and after a series of 2 lectures or something, derived the same Shaw-Kleitman bound. And then he undermined that whole thing, sort of very anticlimactically gave a slit at the level of our YM poset,
I'm probably going to get
a random probabilistic method type argument to derive the same bound. And then, so then I got interested to try this technique to see what this would give, and that's how we managed to get this. But it's still possible that maybe going back to, given we did so much hard work, we got so much information, it was kind of disappointing to get just the, but
because the older formula, I mean, like Larry Sheff's lemma,
yeah.
that's essentially approximating the volume.
Yes.
That's
So,
essentially approximating the volume by discretizing
yeah.
the polytope.
Yeah. And I don't think, we're losing anything there in these asymptotics. It's a question of how well can I approximate that volume. But all that stuff was new to me. It was,
Level one. I haven't listened to this. I don't know enough about it, but it seems to me that maybe there might be a slight volume proof of the two levels.
yeah, that would be nice. Yeah.
that two
That's a
levels.
good question. Right. Right.
Because down the structure of the polygon is only
Yeah. Yeah.
it's also valence. I mean, it's not trivial.
Right.
But still
Right, right.
quite complicated.
But Graham certainly tried using that approach to get an estimate just for the middle two levels of the Boolean lattice. And he couldn't get the same. But my impression is, he learned that stuff to work on this problem in part. He has a tech report that describes that approach. But he's, maybe. But he's not an expert in that, so it's by no means the case that he cannot get the same bound. Yeah, that would be very nice. There was another reason I was interested in the polytope approach, because all this entropy technology and shader, we know only how to make use of for bipartite. Because you condition on one side, you go to the other side, and get done.
Because there is
We have no idea how to.
I was also thinking that to compute the volume of the polytope, if you want to, also your question, what's the complexity of computing?
Yeah.